Hi everyone, and welcome to another video of this channel. So today we will be looking at some problems from the 2020 AIME 1, or rather, the first 5 problems. So problem 1 says, in triangle ABC, which we will draw, so this is triangle ABC, we have AB equals AC, so this triangle is isosceles, and then we also have that point D lies on side AC, and then we also have some sort of E lying on AB, such that DB is also isosceles, like this. So we have a whole bunch of isosceles triangles, so BDC, BDE, and AED. And the degree measure of ABC is some sort of x, and our goal is to find this x. So the degree measure of ABC in this case is the same thing as ACB, right? Because triangle ABC is isosceles. So since this angle right here is x, this angle right here is also x, since BDC is isosceles. And also, this angle is 180 minus 2x, because the sum of the angles of a triangle is 180, and these two base angles right here are x. But then since this triangle is isosceles, this angle right here is also 180 minus 2x. And since the sum of these three angles has to add up to 180, this central angle right here is equal to x. But then, since this triangle is isosceles, we immediately have that the sum of these two angles is equal to 180 minus x. So the sum of just one of these angles is 180 minus x all over 2, so 90 minus x halves. But then this angle right here, this little angle, is the same thing as 180 minus 2x, because this triangle right here, its angles have to sum to 180. So we have that this angle right here is equal to x, but it's also equal to 90 minus x over 2 plus 180 minus 2x. So we can solve for x, and we get that x equals 5/47. So now in typical AIME style, they ask us to sum the numerator and denominator. 540 and 7 are relatively prime, so the answer is 547. Now our next problem. There is a unique real number x such that the three numbers log 8 of 2x, log base 4 of x, and log base 2 of x form in a geometric progression in that order with a positive common ratio. So how can we illustrate this? If we have this logarithm right here, we can multiply it by some r to get log base 4 of x. Then we have log base 4 of x. We can multiply it by r to get log base 2 of x. And so we have to find the number x, reduce it, and sum the numerator and denominator. So let's first start with this equation, since it only has x's being logarithmed, no 2x's. So first there's this logarithm property that says that log base m to the power of n of x equals 1 over n times log base m of x. And we can we can make both sides of these equations the exponent of m to the n, and we can basically prove the identity from there via the definition of the logarithm, like this. But notice that 4 is the same thing as 2 squared. So we can actually factor a 1/2 and simplify this expression right here, just like this. Times r equals log base 2 of x. But now these logarithms cancel, and we have that r is equal to 2. So we can plug that back into the first equation with our logarithms, just like this. But then, of course, we can use the fact that any constant or any number in front of the logarithm can be just turned into an exponent inside the logarithm. So we have log base 8 of 4x squared should be equal to log base 4 of x. So we can raise both sides of the result by 64, so make them the exponent of 64. And that turns into this right here. And then this 2 can be pulled inside again. So we have 8 to the power of log base 8 of 16x to the 4th. And by the definition of the logarithm, that is just 16x to the 4th. Similarly, we can pull this 3 into the logarithm, and we have 4 to the log base 4 of x cubed, which is, by definition of the logarithm, x cubed. So now x is positive, so we can cancel out the x cubed, and we get that x is equal to 1/16. The sum of the numerator and denominator is 17. So now we have a problem from number theory. A positive integer n has base 11 representation ABC. So how would that look like? That means that n can be expressed as c plus 11b plus 121a, right? This is basically the base 11 representation. And then in base 8, its representation is a plus 8c plus 64b plus 512, right? These are all powers of 8. I mean, if it says that the base 10 representation would be 1 BCA, that means that n equals a plus 10c plus 100b plus 1000. But we just have base 8. So now we can equate them. And what is our goal in general? We want to find the least such n. So we want to basically minimize n. So let's just try to find a, b, and c. We have this equation right here from equating the two sides. And we can take both sides mod 7. Now, what is our motivation for taking this equation mod 7? Well, firstly, most of the numbers in here are pretty big, so taking the equation mod something will definitely help reduce the numbers a bit. But why exactly mod 7? Well, we have 3 variables in here. We want to maybe have 2 when we reduce to mod 7. So when we reduce to mod 7, notice that the 7c just cancels out, and the a doesn't have a coefficient because 120 is congruent to 1, mod 7. In other words, when we divide 120 by 7, the remainder is 1. And the same actually goes for 512. So we will have a very nice and clean equation without the c and mostly without the a and without this giant constant when we take the equation mod 7. So that means that a, right, because 120 is congruent to 1 mod 7, is congruent to 4b plus 1 mod 7. That's what this whole equation simplifies to. So now, on a separate note, once again, we want to minimize n. So we have to minimize a, and eventually b and c. So in order to minimize a, we can have a equals 1, right? Then b would have to be equal to 0, and c actually turns out to be negative if we plug back into this equation. So we can't have a equals 1. The next a, that is of this form right here, is a equals 5. So that means b equals 1, and c actually equals to 5. So this is the minimum, these are the minimum digits, basically. So now we want the base 10 representation of n, so we can plug these digits back into this. And we have that n is equal to 621. Okay, so now for our fourth problem, we have that S is some sort of set of positive integers n, and the last 4 integers of n are 2020. So n is equal to some beginning and then 2020. And then we also have this property as when the last 4 digits are removed, so we just have this beginning left, the result is the divisor of n. So, for example, they give an example of 42,020 that is in n because 4 divides 2020. So now, find the sum of all digits of all numbers in S. and they give an example of how this can be done. So first, let's just rewrite this beginning as some sort of number x. So we have from this property right here that x divides x 2020. In more rigorous terms, this can be written as x divides x times 10 to the fourth plus 2020. This. But x obviously divides x times 10 to the fourth, so all we our only restriction is that x has to divide 2020. So 2020 is the same as 2 squared times 5 times 101, which is the prime. So x can be equal to any of these values right here. These are all 12 divisors of 2020. This. Okay. And so now we have that any possible n can be one of these numbers and then 2020 written after it. So the sum of all the digits of all the numbers in S is the sum of all the digits of all the numbers in here plus the sum of the digits of all the 2020s that are the tail ends of all of these numbers. So notice there are 12 numbers in here, which means that there are 12 2020 tails, and the sum of the digits of those 2020 tails is 4 for each 2020 tail times 12, because there are 12 numbers. And now we just sum all of the digits. So 1, this sum right here is 4, plus 2, this sum right here is 2, plus 4, this sum right here is 10, and so on. Now just writing out this giant sum, we get that the answer is 93. So now we move on to our last problem, problem 5. So we have that 6 cards numbered 1 through 6 are lined up. We're just going to draw out those 6 cards. Okay. And they are numbered somehow 1 through 6. And then find the number of arrangements of these 6 cards where one of the cards can be removed, and then the resulting 5 cards will either be in ascending or descending order. So for instance, if this arrangement satisfies the criteria of the problem, we can remove either a 2, a 1, a 3, a 4, 5, or 6, and then the resulting numbers will be either increasing or decreasing. Now, this arrangement is not one of the desired arrangements asked for in the problem, but we can start working on some casework, probably. That's probably the quickest way to solve this. So let the number of the removed card be x. So for instance, if we remove the card number 1, that means x equals 1. And also one quick observation that will really simplify our problem. So notice that the number of arrangements such that when we remove a card, the others are in ascending order, that's the same exact thing as in descending order, because we could just flip the arrangement of 5 cards and they'll be in descending order. So in fact, all we have to do is find the number of cards, of arrangements of cards, such as we remove 1, the result will be in ascending order, and then multiply by 2 to get our answer. Let's proceed with our casework. So we have when the first card is removed, everything else has to be in ascending order, right? All we're counting is ascending order, then we're multiplying by 2. So notice that all the other 5 cards have to be in the order 2, 3, 4, 5, 6 in order for them to be ascending. There is no, freedom for them to move around. So all we have to do is just place the 1 in 6 places. So there are actually 6 total places we can place the 1. Now, if we remove the second card, that's also 6, because all the other 5 cards have to be in the order 1, 3, 4, 5, 6. And now it's a question of where should we place the 2? Here, 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 or here. And so on until we get to x equals 6. So that is 36 total outcomes. However, we overcounted some. Why did we overcount? Well, the answer is actually on the board. 1, 2, 3, 4, 5, 6 we counted once in each of these cases right here. We counted it once when we removed the first card, and the other cards were 2, 3, 4, 5, 6. We counted once here, and then if we remove the sixth card, so the sixth card blue, the second card is red, we have 1, 2, 3, 4, 5, 6. Also, we counted that in this case right here. So actually, we counted this one case 6 times instead of 1 time. And also, we overcounted when we have consecutive digits that are adjacent. So for instance, let's take this arrangement. 1, 2, 3, 5, 4, 6. Here we can remove either the 5 to get an ascending arrangement, or the 4 also to get an ascending arrangement. So we counted this valid arrangement twice, once in the 5 case and once in the 4 case. So actually we have to subtract it once, and then we have to subtract basically one case for each pair of consecutive integers within 1, 2, 3, 4, 5, 6. That's 5 pairs of consecutive integers we have to, correct for. And for each correction, we have to subtract 1. So in total for this case, we have to subtract 5. And then we have our previously discussed 1, 2, 3, 4, 5, 6 case. We also have to subtract minus 5 because we counted 6 times. We want to count it once. Any other case, any other, cycling, like, as in this case right here, any other cycling is not actually a valid combination that we counted in here. So this is all that we have to, correct for. So in total, we have to subtract 10 cases that we overcounted. And so the number of sequences such that when you remove one of the cards, the resulting cards are ascending order is 26. But remember, we have to multiply that by 2. And so we get that the answer is 52 different arrangements. So that's it for this video. I hope you liked it. Thanks for watching, and I'll see you next time.